Hello and welcome to this new video. In this video, I'm going to solve the exercises of chapter 2. But before I start solving the exercises, let me establish a very useful criterion to detect the set of accumulation points of a sequence and therefore the limsup and liminf of a sequence. Okay. Let us start with a very simple case. So consider a sequence of real numbers xn, and suppose that the subsequence x to n of even indices converge to some limit L0, and the subsequence of odd indices converges to another limit L1. Then I claim that the set of accumulation points of xn is precisely the set L0, L1. Why is that? Okay, recall that by assumption, x to n is a subsequence of xn. So its limits is an accumulation point by definition, because the set of accumulation points of xn is by definition the set of limits of subsequences. Okay? Therefore, L0 is an accumulation point, and similarly, L1 is an accumulation point because it's the limit of a subsequence. So L0, L1 is contained in the set of accumulation points of the sequence xn. So now we need to prove the reversed inclusion. So take an arbitrary element in the accumulation points, A. Then by definition, we can find a subsequence x and k. So recall that nk is an increasing sequence of integers, strictly increasing. So we have n1 less than n2 less than etc. that converges to A. Now we split the integers. We can start with 1, it's not really a big deal, or with 0. So we split the integers into two disjoint subsets, the even numbers and the odd numbers. Therefore, the set of indices n1, n2, n3, etc. You can write n star here if you like. So the set of indices is contained in the union of these two partitions. Therefore, there are infinitely many indices k such that nk is even, or there are infinitely many indices k such that nk is odd. Why? Because otherwise there would be finitely many elements would be even and finitely many elements would be odd. Therefore, this set would be finite, right? Because every index is either odd or even. But this set is infinite because it's a strictly increasing sequence of integers. In the first case, call this subset nk1, nk2, etc. in an increasing order. Okay? So let nk1, if you like, be the first index, the first even index, nk2 the next one, and so on. So now we have a subsequence of a subsequence, xnkp. xnkp is both a subsequence of x and k by construction, and the subsequence of x to n because the nkp are even. So nkp, x nkp is a subsequence of the even indices. Therefore, it must converge to both A and L, okay, because x and k converges to A, and x to n converges to L0. So any subsequence of a convergent subsequence converges to the same limit, as you may know. But by uniqueness of limits, we must have A equal L0. Now, the next case, the second case, is completely symmetric. So we have now an increasing sequence nk1, nk2, etc. of odd numbers. So we have now a subsequence of both x and k and x to n plus 1. So it must converge to both A and L1. So again, by uniqueness of limits, we must have A equal L1. So we have two cases. We started from an arbitrary element A in xn, and we proved that it's either L1, L0, or L1. So it belongs to the set L0, L1, and therefore we have the reverse inclusion and therefore equality. Now we can extend this reasoning to a little bit more general case. If instead of even and odd indices, suppose that I have three subsequences of xn, x3n converging to some limit L0, x3n plus 1 converges to L1, and x3n plus 2, this is L2, converging to L2. Then the set of accumulation points is L0, L1, L2. Same reasoning, just copy paste, but instead of splitting the integers into 2, odd and even, we split it into 3. The multiples of 3, 1 plus the multiples of 3, and 2 plus the multiples of 3. So same reasoning. And now we see a pattern. So more generally, if we have a sequence xn such that an integer p which is at least 2, such that xpn converges to L0, xpn plus 1 converges to L1, and so on, xpn plus p minus 1 converges to Lp minus 1, and then the sequence will repeat itself. Then the set of accumulation points is precisely the set of these limits. And therefore, the limsup, which is by definition the biggest accumulation point, is the maximum among these numbers. And the liminf, which is the smallest limit point, is the minimum among these numbers. So this proposition actually that I didn't state in class, but I needed it because in the exercises, because it permits us to solve in a very easy way the first exercise. Okay, so it's a very useful and practical criterion to detecting accumulation points and limsup and liminf. So now we are ready to start exercise 1. First case, we have the sequence -1 to the n times n. Of course, here we can go back to the definition and find limsup and liminf by going back to the definition, but in my opinion, it's easier here to see that actually x to n is 2n, so it tends to infinity, and x to n plus 1 is minus 2n plus 1, so it tends to minus infinity. And therefore, the set of accumulation points is plus infinity minus infinity, and therefore the limsup is plus infinity and the liminf is minus infinity. Now, the second case is a little bit more tricky, because this sequence, now this term is not really a big deal because this term tends to 0, so it does not affect anything. What really matters here is the fact that sine n pi over 2 is not 2 periodic, it's 4 periodic. It's periodic of period 4, not 2. Why? Because if you take x4n, so you get 4n over 2, so sine 2n pi, this is 0. So x4n converges to 0. The next term, x4n plus 1, would be sine 2n pi plus pi over 2. And this would give me 1. So actually, the sequence sine n pi over 2 is 0, 1, 0, minus 1. Right? So period, and then it repeats itself. So x4n plus 1 converges to 1. Right? So we have 0 and 1 now. And x4n plus 2 will be, so this would be 0 actually, as we said, so converges to 0, and the last term is minus 1, so 0, 1, 0, minus 1. So I have actually 3 accumulation points, 0, plus 1, and minus 1, and therefore I conclude very easily that the limsup is plus 1, the liminf is minus 1. Now, of course, this is not the unique way of finding limsup and liminf. You can go back to the definition if you like, but I find this method easier. And of course, you can use it in the exam without any proof. Okay. Now, next example, next case. Actually, if you look at it, we have cosine n pi over 3. Now, once again, this term is not a big deal, and this sequence now is actually periodic of period 6. So this is why we will start with x6n, and so the first so we start by 1. This term, as you said, does not really influence anything. So x6n converges to 1. Next term, x6n plus 1 is cosine pi over 3, because 2n pi plus pi over 3. So the 2n pi actually does not matter. But now we have minus. Now cosine pi over 3 is 1/2, as you know, so x6n plus 1 converges to 1/2. x6n plus 2, so 2n pi plus 2 pi over 3, and this is minus 1/2 now. Okay, plus, so 1 plus minus plus minus plus so on. So you see the pattern here. And if you have 3 pi over 3, so it's cosine pi, it's minus 1. 6n plus 4, 4 pi over 3, which is again minus 1/2, as you may check. And finally, we have cosine 5 pi over 3, which is 1/2. Okay, so now I exhausted everything. And then x6n plus 6 will repeat itself. Okay, so the cosine n pi over 3 is periodic of period 6. Okay, so it's 1, 1/2, minus 1/2, minus 1, minus 1/2, 1/2, and then again it repeats itself. This term is plus minus plus minus plus minus, so but it doesn't really affect anything. And so now by my criterion, I know that the set of accumulation points consists of plus 1/2, minus 1/2, plus 1, minus 1. So once again, limsup is plus 1, liminf is minus 1. Last case, here we have to think a little bit, because by now we know that sine n pi over 4 is periodic of period 4, and cosine n pi over 3 is periodic of period 6. Therefore, the product is periodic of period 12 this time. Okay, so this is why I have to compute x12n, x12n plus 1, and so on, x12n plus 11. And if you do that, please do it. I will not do it here. You will find these values 0, 1/2, 0, 1, 0, 1/2, 0, minus 1/2, 0, minus 1, 0, minus 1/2, and then it repeats itself. So the period is 12. So once again, the set of accumulation points consists of 5 values, 0 plus or minus 1/2 and plus or minus 1. And once again, limsup is plus 1, liminf is minus 1. Okay, if you don't believe me, please check that. And if there is an error, don't panic. I will correct it, but the reasoning is correct. Okay. Now, maybe you may find a quicker way to see that the limsup is plus 1 or minus 1, but I think this method is systematic. So it's easier to use. Okay, so this concludes exercise 1. Next exercise, adjacent sequences. So we have the first sequence un given by 1 plus, so the sum of the inverses of the cubes of integers. Now, if you already studied series, then you know that this series is convergent actually, but its limits is not, there's no formula for the limits actually as involving the usual constants. Okay, so unlike the case 1/2 squared plus 1/3 squared. So, but we know that it's convergent actually. But this exercise does not assume that you should know something about series. We have to check by going back to the definition that the two sequences are adjacent. So we have to prove what? That un is increasing, vn is decreasing, un is less than vn, and the difference tends to 0. Okay? Now, most of these results are trivial. Now, because un plus 1, the difference between un plus 1 and un is not just 1. Sorry, there's an error here. This is 1 over n plus 1 cube. Please correct that, but doesn't change anything. So un plus 1 is strictly bigger than un. So because each time I'm adding a positive number, so un is increasing. This is very easy. Now, the fact that Vn is un plus 1 over n squared implies that Vn is bigger than un because I'm adding a positive number, so this is trivial. And the same relation actually implies that the difference, so this is equal here, the difference tends to 0, so trivial. So I start with the trivial, and I have the less trivial is the fourth point, so this is why I left it to the end. I just do the difference between Vn plus 1 and Vn. So if you do the so you write Vn plus 1 equal Un plus 1 plus 1 over n plus 1 square, and the same, and you subtract. Un plus 1 minus Un is precisely this cube, okay? And this is the difference, and so you may check that this is the difference if you write everything, okay? If you cancel, so all these terms cancel actually. And so this is the difference. Now it's not clear why this is negative. So the easiest way is to reduce to the same denominator. And if you do this, you will convince yourself that the numerator is minus n squared minus 3n minus 1. And this is something negative because n starts from 1 actually. Okay, so that's it. This is very easy. Next exercise, also about adjacent sequences. So now we have two sequences defined by induction in the same way. Okay, but they are interdependent. So Un plus 1 depends on Un and Vn plus 1 depends on both. Now, first thing that you may prove is that everything is well defined. Why? Because we are taking square roots. Now, when we take square roots, we need to ensure that what is inside is positive. This is not a big deal because we start with positive values, and when we iterate, we still have positive square root of positive values, so everything is, and here we have a sum, so everything is positive. So it's not really difficult to prove that both sequences are well defined. Now, let us prove by induction that Un is less than Vn, so we start with the easy part. For n equals 0, this is equivalent to saying that radical AB is less than the sum over 2. And this is true because if I subtract radical AB, I get a perfect square. Okay, or just multiply by 2 and make the difference. We have A plus B minus 2 radical AB, and this is radical B minus radical A squared, and this is something strictly positive. So the claim is true for n equals 0, and now we assume that the claim is true for some integer n. And we once again use this inequality. Okay, and this inequality means that Un plus 1 is less than Vn plus 1. So by induction, Un is less than Vn. Now, why Un is increasing? Just make the difference and factor by radical n. By the first point, radical Vn is bigger than radical Un, so the difference is positive. This is positive, so therefore Un plus 1 is bigger than Un. Now Vn is decreasing. Just go back to the definition. Vn plus 1 is the sum over 2. And if you reduce to the same denominator, you get Un minus Vn over 2. And by the first point, this is negative because Un is less than Vn. Now, it's not really clear why the difference tends to 0. So we reason in an indirect way. What do we have now? We know that Un is increasing, and it's bounded from above by any term. So take V0. So V0 is an upper bound of Un. Therefore, Un is conversion to some limit L. And similarly, Vn is decreasing and bounded from below, for example, by U0. So it's conversion to a limit L prime. Now, if you consider the relation Vn plus 1 equal Un plus Vn over 2, now I know that both sequences are convergent. So this converges to L prime, this converges to L plus L prime over 2. And therefore, if you solve this equation, you'll get L equal L prime. So the difference tends to 0, right? But now, of course, you can use the other relation, if you like, to prove that L equal L prime, same thing. Maybe you may find another proof of this, but I found that this is the simplest way to prove that the difference tends to 0. And that's it. So this concludes exercise 3. Fourth exercise, Cauchy sequences. So once again, if you already know series, you may know that this series is divergent and this series is convergent. But the purpose of the exercise is to prove directly by going back to the definition that this sequence is not Cauchy and this sequence is Cauchy. Okay, now this is not totally trivial. We have to negate the Cauchy condition. So one way is to consider the difference x2n minus xn. Why? Because if you write this, you go back to the definition, of course I can get rid of the absolute value because the sequence is increasing, right? So x2n is bigger than xn. So when I simplify, actually, I get what? I get the sum from n plus 1 to 2n. So I write it as 1 over n plus 1 plus 1 over n plus 2 up to 1 over 2n. And now, how many terms do I have here? I have n terms, and the smaller one is the smallest one is 1 over 2n, right? Because because n plus 1 is less than n plus 2. Okay, or if you like, n plus 1 is less than 2n. So the inverse of 1 over n plus 1 is bigger than the inverse of. So all terms are at least 1 over 2n, but I have n such terms. So it's easy to see that this sum is strictly bigger than n over 2n, which is 1/2. And this negates the Cauchy conditions, actually, because if xn was a Cauchy sequence, then we would have x to n minus xn should be less than any epsilon I like for all n big enough. So if I choose n big enough, from the one hand, I get the difference is bigger than 1/2 and less than epsilon, so I should get 1/2 less than epsilon, but epsilon was arbitrary. So in particular, if I take epsilon equal 1/2, I get a contradiction, or anything smaller. Okay, so therefore, now I agree this is not completely trivial to find this, because you may try, if you try xn plus 1 minus xn, this tends to 0, so you will not find a contradiction, actually. But so this is why you have to take something bigger, significantly bigger, because one term is not enough. But if you take enough terms, then this will work. Of course, it works with 3n if you like. For the second one, we do the difference. Now, instead of writing ym minus yn, it's possible to write yn plus p minus yn. So just write m, assume m is bigger than n. It's not a big deal because among the two numbers n and m, one is bigger. So call the bigger one n plus p. Right? So now we want to prove what? We want to make this less than epsilon, right? For n big enough, for n large enough. So if you write yn plus p, go back to the definition and subtract yn, then once again here you have a sum 1 over n plus 1, so it's 1 over k squared if you like, k from n plus 1 to n plus p. So I have here actually p terms. Here actually we could say that this is less than p over n plus 1 plus p or n plus 1 squared, but this is not very helpful because p could be also very large. So we do a trick. So since n plus 1 squared is bigger than n times n plus 1, right? So the inverse, take the inverse, we get the opposite, the reverse inequality. So 1 over n plus 1 squared is less than 1 over n times n plus 1. And this is something that convenient because we can split it. We can use simple fractions if you like. We can write this as 1 over n minus 1 over n plus 1 because if you reduce to the same denominator, you get this result. And this is what we call actually a telescoping sum, because if we write also 1 over n plus 1 squared as 1 over n plus 1, so it's less than 1 over n plus 1 minus 1 over n plus 2, same thing actually. So for each term, each term is less than the difference of two consecutive inverses. And when you do the sum, you will have simplification. So the first term is less than this difference. This is the first term. Second term is less than this difference, and so on. The last term is less than this difference. But when we do the sum, we have simplification. So this cancels with this, and so on. And we are left with the first one, 1 over n, and the last one is 1 over n plus p, and this is less than 1 over n. And that's it. If now n is big enough, for example, bigger than 1 over epsilon, we have yn plus p minus yn is less than epsilon. And this is true independently on p. Okay? Or if you like, we can write this as ym minus yn less than s. So they are really equivalent. So as a takeaway, actually, and by the way, so this proves that yn is a Cauchy sequence. So therefore, it's convergent. And there are many ways to prove that the limit is pi square over 6. So we will probably prove this next year. Okay? But you should know that the limit is pi square over 6. Okay? Now, so we have now two ways to prove that a sequence is Cauchy. So either you go back to the definition, ym, so you just estimate the difference between any two terms for large indices, or you fix one, or you prove that yn plus p minus yn tends to 0 as n tends to infinity for any p. Okay, so this is a convenient way of proving, so this is the takeaway. So un is a Cauchy sequence if and only if un plus p minus un tends to 0 as n tends to infinity, and this is independently on p. So same thing, actually. Instead of working with the epsilon, maybe sometimes it's easier to have this case. And next exercise is also about a Cauchy sequences, and the technique is very interesting here. Now, you may prove actually that un is increasing. Yeah, actually, it's easy to see that un is increasing, right? Because this is bigger than un. And you may prove that un is bounded from above, and therefore it's convergent, therefore it's Cauchy sequence. But the purpose of the exercise is to prove directly by going back to the definition. Okay, so let us start by estimating the difference between un plus 1 and un. And of course, this is something positive because you can get rid of the absolute value. So when I do this difference, of course, as you may know from high school, you multiply by the conjugate of this expression. And so you get rid of the radicals in the numerator, and you have a simplification now. Okay, now, so the numerator is 1 over 2n, and the denominator, because everything is positive here, as you may check, so the denominator is bigger or equal than 1 radical of 1 over 2n. So therefore, the quotient is less than 1 over 2n divided by the radical of 1 over 2n. And I can write this as 1/2 to the power n over 2, or if you like, 1 over radical 2 to the n. Same thing. Now, of course, this tends to 0, but I know that this is not something new, actually. But this is not sufficient to prove that un is a Cauchy sequence, okay? Because I have to consider un plus p minus un. But this is a good starting point, because if I write un plus p minus un as un plus 1 minus un plus 2 minus un plus 1, or you can use the triangle inequality if you like. But here we have exactly equality, right? Because we have a simplification, okay? So you just add and subtract consecutive terms. So we start with minus un, add and subtract un plus 1, add and subtract un plus 2, and we are left with the final one, okay? Now, the first difference is actually less than 1 over radical 2 to the n. The next one, this difference is less than 1 over radical 2 to the power n plus 1, and so on. And the last term is less than 1 over radical 2 to the power n plus p minus 1. Okay, so if you do the sum, you find this. Now, this is good, because now we can compute, or at least we can estimate this, because this is a geometric sequence of ratio 1 over radical 2. So if you factor by 1 over radical n, so we get 1 plus 1 over radical 2, etc., up to sorry, this is p minus 1. There's no n here. It's an error. So it's p minus 1 because we factored by 1 over radical to the n. And this has a formula. 1 plus q squared plus q to the p minus 1 is 1 minus q to the p over 1 minus q, as you may know. Or the other way around. qp minus 1 over q minus 1, same thing. But I wrote it here because I need to get something positive over positive, because q is less than 1. Now, the numerator is less than 1, of course. I don't care about that p. So I get 1 over radical 2 to the n times 1 over 1 minus 1 over radical 2. So if you reduce to the same denominator, you get radical 2 minus 1 over radical 2. So it's a constant. I don't care very much about what it is. It's constant. So, and now, so this is independent. This estimate is independent on p. So for every p, this term tends to 0. And according to what we said, un is a Cauchy sequence. So you can make this less than any epsilon if you like, if you take n large enough. Okay, it's not really necessary to find the n in terms of epsilon, because we know that it tends to 0. Okay. So this technique is very important actually, and we shall see it next year in another context. So please, if there's an error, there's no n here, and there's no parentheses here. Okay, but the result is correct. Okay. Exercise 6, sequence is defined by induction. So we give a positive number, starting number u0, and we iterate in this way. Un plus 1 equal 1 plus un squared over 4. And you have to study the conversions of this sequence and draw a cobweb diagram as we did in the last week. But you have to distinguish between 3 cases. Okay, so let us start. Okay, first of all, let us write it in the usual way. Un plus 1 is a function of un, where f is this function. So we start by drawing this function and finding its fixed points, because we know that if such a sequence is convergent, then its limits must be a fixed point, as we know, because it's continuous here. So we find that there's only one fixed point, which is 2, and the graph of this function is tangent to the first bisector at the point 2. So if the sequence is convergent, the limit must be 2. And if we start with something less than 2, as is suggested by the hint, and we do the iterations, then we see that we must converge to 2. Okay, but let us prove that algebraically, because the picture is not a proof. So, yeah, how do we know that un is convergent? You must prove that un is increasing and bounded from above. Okay, in this case at least. So, if we do the difference between u1 and u0, you do the computation. So you get 1 plus u0 squared over 4 minus u0. And this should give you 1 over 4 times u0 squared. If you do so, or minus u0 squared, same thing, if you do the difference. So just algebra, and this is something positive. So u1 is bigger than u0, and we know that since f is increasing, then the sequence is increasing. We proved that in the lectures, and if you can reprove it if you like. It's not really difficult, because by induction, if u1 is bigger than u0, apply f, then you get u2 is bigger than u1, and so on. Now, but I have an extra assumption here, is that u0 is less than the fixed point. So we prove by induction that un is less than 2. So the claim is true for n equals 0 by assumption. If it is true for some n, then apply f, because f is increasing. If un is less than 2, then f of un is less than f of 2. But f of 2 is 2, because 2 is a fixed point. So I get un plus 1 less than 2. So now we have all the ingredients to conclude. We have an increasing sequence, which is bounded from above, therefore it's convergent, and the limit must be 2. So this confirms the graph, the cobweb. Now, the case u0 equal 2 is really trivial, because if you start at a fixed point, the sequence will be constant. Okay, because if u0 equal to f of u0 equal f of 2, so u1 equal f of 2, which is 2, and so on. So by induction, un is constant. So this case is not interesting, and the cobweb is just a single point. So we have also conversion in this case. Now, the last case is a little bit tricky, but let us start by doing an experiment. So we start with an initial value bigger than 2 and see what happens. So the sequence seems to be increasing without bound. Okay? And now we have to prove that. Okay. Now, we already know that u1 is bigger than u0 actually, and this was because if you do the difference, you will find something positive. And so this is irrespective if u0 is less than 2 or bigger than 2. Okay. So this is just because if you do the difference, you get and you have a complete square, and okay, you get the complete square. Now, since f is increasing, we conclude that un is increasing because you just apply f. Okay. And now let us prove that un is divergent, as suggested by the cobweb. Okay. I will prove that un is divergent in 2 ways. First way, we reason by contradiction. If un was bound from above, then un would be convergent because it's strictly increasing. But if it's convergent, then it would converge to the unique fixed point, which is 2. But this is a contradiction because un is increasing, so un is at least u0, and u0 is strictly bigger than 2. So un cannot converge to 2. There is a barrier here. So therefore un is unbounded, and therefore from above, and therefore it's divergent because the convergence series is bounded, as you may know. Convergence implies boundedness. But this is less precise than the second way. In the second way, you just estimate the difference. Okay? If you compute the difference by going back to the definition, so you just write un plus 1 is 1 plus un squared over 4, and so you get this complete square. Okay? And we know that un is bigger than u0, then this difference is at least 1 over 4 u0 minus 2 squared, which is something strictly positive. Call it a. So un plus 1 minus un is bigger than a constant a. So each time I'm adding a constant a. So it's easy to prove by induction that un is bigger or equal than u0 plus n times a. And therefore un tends to infinity because this tends to infinity. This is more precise because saying that a sequence tends to infinity is more precise than saying it's unbounded or divergent, because it could be divergent, unbounded, but does not converge to infinity. Think of something oscillating, right? Okay, by the way, you may prove, if you like, that if un is unbounded from above, then there is a subsequence of un convergent to plus infinity. Okay, this is a very useful result. Okay, so this concludes exercise 6. Exercise 7, similar, but now we have a decreasing function actually. So we have un plus 1 equal f of un, where f is 1 plus 1 over x, which is a decreasing, as you know. So by the lectures, we must compute f of f. So f of f, as you may check, it's 1 plus 2x over 1 plus x. And if you try to find the fixed points of f, you'll find 2, because you get a quadratic equation. I will not write it, you do it. You will get 2 roots, 1 plus radical 5 over 2 and 1 minus radical 5 over 2. Now, since we are starting with a positive initial value and f is positive, we disregard the negative fixed point, okay, because we are very far from it. So there's only so call them anyway. So call the first fixed point, the positive fixed point, call it L, and the negative fixed point, call it L prime, because you may need it actually later. But everything will be around L, and because we cannot reach L prime, because if you start with something positive, if u0 is positive, un is positive. Okay, so if it converges, then it must converge to the positive fixed point and not the negative one. And of course, you may notice that L is also a fixed point of F, because if you find the fixed point of F, you'll get actually 2, the positive one being that L, this one. And this is the graph of F, so it's decreasing, and it meets the first bisector at the point LL, where L is 1 plus radical 5 over 2. Okay, so let us distinguish between 3 cases, the second being trivial. So first case, let us do some iterations here. So we start with U0 less than L, and we do the iteration. So we see that at the next iteration, U1 is bigger than L. So if you start at the left of L, we'll be next time at the right. And now if you repeat that iteration, we'll be then at the left once again. So you see, we have an oscillating sequence which converges to the fixed limit point, the fixed point. Okay, so we see here that we may extract 2 subsequences: the sequence of even indices and the sequence of odd indices. One is increasing, one is decreasing. So this is what we see here, and we can prove that rigorously. Now we know that actually the sequence of even indices are actually so U2 is actually f of U0, and U4 is f of U2, and so on. So we have to study the sequence Vn plus 1 equal f of Vn. Okay, and f of f is increasing, right? Because decreasing of a decreasing is so we know that actually. Now, if we want to compare U0 and U2, we have to study the sign of f of x minus x, and this is not difficult. Yeah, this is just an error of computation, not of typing. So this is 1 plus 2x over 1 plus x minus x. And if you reduce to the same denominator, sorry for that, yeah, there's an error here, but if you reduce to the same denominator, please check that, you will get minus x squared plus x minus 1 over 1 plus x. And if you factor that, you will get minus in the numerator minus x minus L prime divided, this is divided by 1 plus x. Okay, so this is the numerator here. So it's easy to study the sign of it. Between the roots, actually it's what? It's positive, right? And outside the roots, it's negative, because you have the minus sign here, right? So just, you can do a table, but just please rewrite it properly. But the conclusion is right. So the difference is positive between the roots, so between L prime and L, but here we are, of course, bigger than 0. So if x is less than L, the difference is positive, and negative otherwise. Okay, so this result is correct, but here it's just typing errors. Okay, so since now we are in the case U0 is less than L, then when we apply f of f, we get U2 is bigger than U0. So, and since f of f is increasing, then we know that U sub 2n is increasing. Okay, and it's easy to show by induction, as we did in the previous exercise, that U to n is less than the fixed point. If you start with an initial value less than the fixed point, then all the sequence will be less than L. So this is easy to prove by induction. Everything is correct except this formula here. But the numerator is actually just, okay? And so what do we have now? We have an increasing sequence which is bounded from above, and therefore it's convergent. And now, yeah, there's also an error here. If U0 is bigger than L, everything is completely symmetric, actually. Yeah, sorry, we are still in this case. the sequence, it's easy to prove that the sequence of odd indices is decreasing, and this was clear on the Cobweb actually here. Okay, so if we start with 0 here, right? So the sequence, so U0, U2, U4, etc., and U1, U3, U5. Okay, so U to n is increasing, U to n plus 1 is decreasing, right? So, and this is easy to prove by induction. So therefore, and you can prove that U to n plus 1 is bigger, is bounded from below by L. Therefore, both subsequences are convergent to the same limit, and the same limit must be L because it's the positive fixed point of f of f. Now, if U to n and U to n plus 1 converge to the same limit, then Un converges to the same limit L. This is not difficult to see. Okay, so, and it was clear from the picture. Okay, so this concludes the case where U0 is less than L. Now, the case U0 is bigger than L is completely symmetric. Okay, the case U0 equal L is trivial because we have a constant. The case U0 is bigger than L is completely symmetric to case 1. In this case, U to n is decreasing and U to n plus 1 is increasing, and both converge to L. So the whole sequence converges to L. Okay, and this is clear on the Cobweb actually. Because if we started from here, next time will be here and so on. So we'll oscillate, right? So it depends where you start, but the behavior is the same. We have convergence to, so I didn't write it actually, but the whole sequence converges to the limit point, but in an oscillating fashion, not in an increasing or decreasing way. Okay, so please excuse these small errors, typing errors, and okay, so this concludes the exercise of chapter 2. Thank you for your attention, and in the next video we'll start chapter 3.